Okay, thank you for coming to this third lecture. So I want now to concentrate on one case of Gale duality, which is related to this geometric proof suggested by Mukai for proving that some of these blow-ups are modern spaces. So this is a case, a particular case of Gale duality. Yes, where we are looking at P2 blown up at n plus 4 points. So here I assume very general. Gale duality requires only linearly general, and you will get some mileage out of configurations of not very general points, as Hal mentioned. And then this is Gale dual to Pn blown up at n plus 4 points. So these are the Gale dual. So I'll only talk about this now. And I want to look at the basis for the Picard group of S, as usual, hyperplane class of a line and then exceptional divisors. So I'll denote this with small letters. And then on X, the same classes with capital letters. Okay, so the idea is that you want to realize this X, the blob of Pn at n plus 4 points, as a moduli space of so-called L-stable vector bundles on S. So I'll explain, I'll give a crash course on these next. On S. Yes, and so the idea will be that all the small modifications that sometimes you get all the small modifications of X also as moduli spaces just by picking a different line bundle L on the surface. So the small modifications will also be moduli spaces. Here L is an ample line bundle on S. Okay, and the idea was, again, just the idea is that you want to look at some special cases, special types of extensions. These are on S. Yeah, so we're looking at, if I denote, just for simplicity, I call small e the sum of all the exceptional all the exceptional divisors, the blob of P2 at n plus 4 points. Sorry, there are n plus 4. Okay, we look at extensions of type, so there are extensions of line bundles on the surface. And then we said that this is so extensions like this up to, non-trivial extensions like this up to scaling form a projective space of dimension n. And then just for making the first chunk class of this vector bundle the anti-canonical, so Mukai twist here with O of H. Yeah? So just twist with the class of a line, and then that makes the first chunk class of E. Yeah, so this is E twisted with 1, but now here C1 is minus K, so 3H minus E. This is a rank 2 vector bundle. And again, it's not hard to see that the second churn classes, which is the product of these two divisor classes, this is 2. Yeah, so this is the numerical invariants that we're going to look at. Okay. Yeah, so what are L-stable sheaves? Okay, so if you have a torsion-free sheaf on S, so I will do the case that interests us, so rank 2. Okay, this is called Giesecker L stable. Or just L stable. Okay, if for every subsheaf of rank 1, so here I will always assume that the subsheaf is such that the quotient is torsion free. This is a rank 1 subsheaf. Then we want to look at the Hilbert polynomial of these objects, and scaled by the rank, we want the Hilbert polynomial of f0 to be less than the Hilbert polynomial of f. Yes. So precisely, this is, L is an ample line bundle. Okay, and I take powers of a twist. Yes, I look at the Hilbert polynomial of a sheaf. This is a polynomial in N. And generally you divide by the rank. Here the rank is 1. I do the same thing for f. Here I divide by the rank, which is 2. Yeah, so I call this to be L stable if this is true for n is for n sufficiently large. And then semi-stability would mean just to allow here equality. So L semi-stable would allow here equality. And then there is another notion of stability, which is coming from the slope, which mimics what happens for curves. Yes, so we call f to be mu L stable. Or semi-stable. If for any rank 1 subsheaf, you have that the slope of f0, which is by definition, yes, the degree with respect to L. So you take the first Chern class of f0 intersect with L. Yes, and then divide by the rank, which is 1. I want this to be less than the slope of f. And then allow this to be an equality for mu L semi-stable. Okay, so I should say that this is all the notions of stability, they arise essentially from GIT. Yeah, so for the correct GIT problem, this is exactly the translation of the GIT stability explicitly. And so for curves, the situation is simpler. Yes, you can talk directly about degree of a vector bundle and the rank, and then the stability is exactly the slope stability. And then in higher dimensions, you need to fix a polarization in order to talk about degree. Or Hilbert polynomial. And this is a vast subject that started, I guess, with the work of Narasimha and Seshadri for curves. And then for surfaces, many people studied this. So Maruyama, Simpson, and this is all very old theory. Yes, it's nowadays there are better ways to think of stability, like a Bridgeland stability. And, but so I'm going to do the classical theory. And as I said already, this begs the question of what you can get more than what we get here by working with a different stability. Okay. So, again, as I said, I'm going to remind you some of the properties of this. Yeah, so now we're doing surfaces, which is the next simplest case after the case of curves. The way we are working with it here, it's a very classical theory on surfaces. But already you kind of see the complications that arise. So remark, the slope stability is the strongest. So why do you have two notions? So this will imply the L stability, just because the slope is what appears in the Hilbert polynomial as the dominant coefficient. And of course, this is stable implies always semi-stable. And then else Gieseker semi-stable will imply mu slope semi-stable. So this is the weakest. And then we'll need to fix the numerical invariance just to get a proper moduli space. To get projective variety, yes. So I will fix exactly the numerical invariants that appeared in our extensions. Yes, we're trying to realize those extensions as some stable vector bundles. So the rank is 2. First rank class is minus k. This is a bit artificial. Yeah, we just we could have not twisted, but okay. And then C2 is 2. So I'm going to refer. I will always look at these numerical invariants. Okay, and then the theorem, which is summed up, is that there are projective varieties which parameterize stable objects. So I'll call them projective moduli spaces. So there is I'm going to denote ML, the moduli space of Gieseker, L semi-stable, torsion-free sheaves, with our numerical invariants. So there will always be here an open set which parameterizes stable objects. Okay. Okay. And then there is a. So far I was vague about what moduli space means. Yeah, so I'll say a bit more about that. So there is also a space which corresponds to mu semi-stable. Again, torsion-free sheaves with the same numerical invariants, and then here also you have an open set of stable with respect to slope-stable objects. Okay, so this is the space that is better behaved in the sense that it is a coarse moduli space for the functor of L semi-stable torsion-free sheaves with the given numerics and modulo what's called S equivalence. So I'll just write it like this. So if I have two objects that represent the same stable point in the Gieseker moduli space, this can happen if and only if f and f prime are isomorphic. So this is an ideal situation. And then for the semi-stable, strictly semi-stable points, this is a bit different, but it's not too bad. Yeah, you can say that. So I'll write it like this: the graded pieces of the Jordan-Holder filtration are the same. So I will not write the definition of this, but this means that if you have a semi-stable object, then there is always a filtration, not unique in general, such that successive quotients are stable. And then you take these successive quotients as your graded pieces of your Jordan-Holder filtration. So in practice for us, what this will mean is that for this rank 2 case, it just means that if it's not stable, then I can find a destabilizing object. So a torsion-free subsheaf here of rank 1, and then with a rank 1 quotient. And then these will be stable, and now torsion-free sheaves on a surface are of the form line bundle tensor with an ideal sheaf of a zero-dimensional scheme. So it's a fairly simple situation. And then these are the pieces of the Jordan-Holder filtration. So that is to say we are representing the direct sum of these two will give the same object in the moduli space. So same here. Yes, this is also sum. Okay. So that's for Gieseker stability. For the slope stability, it's a bit more complicated. So there, the stable locus will be a coarse moduli space for the same problem. This is going to be a coarse moduli space. And then if I take 2 points here, so these also have to be isomorphic also because we said mu stable implies L stable. But okay, it's not clear a priori that, yeah, so if these represent the same, it's not clear how to compare the moduli spaces, but they do compare. But I'm saying well, that is true. And then there is something similar to this, but it's more complicated. And yeah, so there are already complications that appear here. And in general, yeah, there is a morphism from the Gieseker space to the slope stable moduli space. Okay. And I should say in general, remark, these are not irreducible. And so then there is you can say you have a deformation theory which behaves, well, so there are some things you can say. So there is a criterion for smoothness. So if I take a point, a stable point, then the abstractions for this to be a smooth point are in the x2 of f and f. Yeah, so if this is 0, then this will be a smooth point. And the tangent space is given by the x1. So this will be of dimension given by the dimension of that. Okay. And then I should have said this earlier, that the stability ensures that you have as few as possible automorphisms. So in this case, for stable sheaves, there is only scaling that as possible automorphisms. So. Okay. All right. So, so the idea is that when you take a polarization, an ample line bundle, which is K negative on our blow-up of P2, these spaces are actually well behaved, and they fit into a well-studied theory of these moduli spaces from the 90s. Yeah. So, for example, if you have L ample, as I said, with L times K negative, then if you take a stable torsion-free sheaf with respect to L, then this will be smooth. And of dimension n. Okay, so this is a simple calculation. So let me just do it, maybe just for get a sense of what goes in these kind of calculations and where does this condition come in. Okay. Okay, so proof. So let me assume for simplicity that F is a vector bundle. It can be done without, but okay. Assume F is a vector bundle. Okay, so then we're trying to show that the x2 of F and F is 0. So by self-duality, this is the same as looking at the space of the home between F and F tensor K. So we're trying to show this is 0. And then an easy observation is that F is, if F is mu L semi-stable, if I tensor with a line bundle, the same will be true. And so then another observation is that if you have a non-zero morphism between mu L semi-stable objects, and the slope have to increase. Okay, so for us, it will come down exact. This is not going to be true just because K times L is negative. So this is C1 F tensor with K, intersect with L, and then same thing for F over 2. So this is exactly, this F is rank 2, so this is C1 of F plus 2K, so it's exactly K times L. Okay. Okay, so, and then, okay, it's a calculation of, this you can compute the Euler characteristic to be, this is a Riemann-Roch calculation from the numerical invariants. This is 1 minus n. And then that gives you exactly the home space is one-dimensional, and that gives you the dimension of the x1 is n. So this will be a smooth of dimension n. Okay. So even in this situation, when K times L is negative, the moduli space can be empty. So just a remark, which is proved in similar way. If L times K is negative, in order to have a non-empty moduli space, say for slope semi-stable, you need, for example, that 2h plus k times L is bigger or equal than 0. And such line bundles, there are line bundles like this. There are line bundles that do not satisfy this, or even on the when they intersect K negative. Yeah, so, for example, L is, if I take a large D and I look at DH minus E, for D large, this will not satisfy this. Yeah, so that means the moduli space will be empty. Okay. Okay, and this condition is related a bit to the condition that that our vector bundles admit non-zero maps into O of H. Yeah, so in some way, so I didn't write down the calculation here, but it will involve showing that the home space between the vector bundle and O of H is non-zero. So it suggests somehow that all these objects come as extensions like this. Okay. Okay, so then, yeah, so we're going to study now how does the moduli space vary with when you vary L. This is like a natural problem. in GIT in general. Do these objects tell you more about the geometry of one of the spaces? And this is, again, it's a classical subject in the moduli theory of vector bundles. So it's like from the 90s. It was by Goethe, Ellingsrud, Goethe, Friedman, Chin, Maruyama. So it's extremely classical. And the results, which are several sets of results around the same time, essentially all say the same thing, that as long as the polarizations are essentially on the k negative side of your surface, it can be formulated like that, then the behavior is as nice as it can be. So looking at variation of L ample. Yeah, so what does this give? What does all these moduli spaces? How are all of them related? Okay, so the key observation there is that in order to pass from a line bundle for which you have a stable object to a line bundle where the same object is not stable, you have to pass through strict slope semi-stability. So that means something that is slope semi-stable with respect to some ample line bundle, but not stable. So this means mu L semi-stable, but not stable. So there is an object, a subsheaf of rank 1, which has exactly the same slope. And now again, for our situation, rank 2 on a surface, on a smooth surface, you must have this Jordan-Holder filtration, which I already said the rank 1 torsion-free sheaves are of this type of a line bundle. This is by the ideal sheaf of a zero-dimensional subscheme. And then the fact that the Chern class of F is minus k, that forces the quotient to have a first Chern class minus k minus d. And then this is again twisted by, so there are two zero-dimensional subschemes. Okay. It appear. Okay, here the slope is given by the first Chern class, so it's d times L. Here the slope is the first Chern class of F, which is minus k times minus k multiplied with L divided by 2. So in order to have that this is has the same slope as F, these quantities have to be equal. So L has to intersect 2d plus k for some divisor d in 0. And then there is also a constraint on the length of these zero-dimensional subschemes. Yeah, so those contribute to the second Chern character. So in the end, what you get is you get 2d plus k intersects L in 0. And then from the second Chern character calculation, you get that the length of these zero-dimensional subschemes, they have to sum up to d squared plus d times k, the product of the two C1s of these torsion-free sheaves of rank 1, plus the second Chern character of F. And now these are lengths of zero-dimensional subschemes. This has to be bigger or equal than 0. Okay. All right. So this says that basically in order to have such an object, a strictly semi-stable, mu-L semi-stable object, you need to pass through these hyperplanes, some hyperplanes defined by classes of the form 2d plus k, and then there are some constraints on the self-intersection of d, on the intersection of d with k. Now, remark. So this is what makes the k negative side of the ample cone even nice, better behaved is that actually you can prove this has to be actually equality here. So it has to be 0 if k times L is negative. Yeah, then claim that this has to be an equality. And so in particular, that means that Z1 and Z2 are empty. So strictly semi-stable objects will arise exactly from extensions of line bundles. Okay, so this is, again, it's not hard to see. It's a calculation of the Euler characteristic of minus d. So this is d squared plus d times k over 2 plus 1. It's a rational surface. And then if k times L is not positive, then as we know, 2d plus k has to intersect L in 0. So if I have these, yes, these two conditions actually imply that minus d has no sections, because d minus d times L is less or equal than 0. Right? We said so 2d times L is minus k times L. That is positive. So minus d times L is negative. Same way, H2 has to be 0 too. So by self-duality, this is H0 of k plus d. And this is also 0 because it intersects L negatively. Yeah, this is the same as k plus d times L. Okay, so that means that this number here is actually, this is actually negative. Okay, so that's exactly, it means equality. Okay, so, all right. Okay, so there is a general theory of how to study this change of stability. Yeah, so these divisors cut what are called stability walls. So this is in general for any surface. You have that. So stability walls. So these are in the Néron-Severi vector space. Yeah, so in general, they are given exactly by these hyperplanes cut by a divisor of the form 2d plus k, with the property in general that d squared plus d times k has to be bigger or equal than minus 2. Okay, so there are countably many such things. And also, yes, we want to really be that there is an ample line bundle there. So I want also to know that there exists a line bundle ample on this hyperplane. Okay. Yeah. So then I call this k negative. If I can arrange that this line bundle is also k negative. Okay, and now these will be cut by classes where I have equality here. And so let me give a name for these classes. So we call class D to be a divisor, the Picard group of S is a rational, numerical rational class if it satisfies a type of adjunction formula, d squared plus d times k is minus 2. So it behaves like a curve with a genus 0. Okay. So it would be interesting to classify these, but we don't know classification of that in general. So there are some special cases where you can classify, and these are the ones that appear for on-del-Pezzos, essentially. So I'll say about that more later. And also, note that if I have such a numerical rational class, then minus k minus d is also a numerical rational class, and defines the same wall. Yeah, so okay. So then, in general, yes, you want to look at the stability. Then will not change unless you cross one of these walls. So we have what's called stability chambers, which are the connected components of the complement of these hyperplanes. So you look in the ample cone, or even the Neff cone, and then you look at the complement of the stability walls. So there are countably many of these, and so the connected components are called chambers. And then on a chamber, actually all the notions of stability coincide. So if I have any element in a chamber, then slope stability is the same as semi-stability, but that means also they are all equivalent. Okay, so the moduli space will, we can prove the moduli space will also be the same. Okay. Are there any questions so far? Okay, so I'm going to denote for a chamber, I will call this way the moduli space corresponding to that chamber for any L. And then a remark is that so now we want to look at these chambers and see what they tell us, and how is this related to our blow-ups. But the remark here is that actually the divisor D could be 0, and so in other words, the hyperplane cut by the canonical class is also a wall if you have at least 10 points. Yeah, so this is equivalent to saying that there is an ample Lyman on the k positive side. And that is exactly saying that the ample cone is not contained in the k negative side, which is to say that the anti-canonical is not effective, not pseudo-effective, and that's by Kleiman's criterion. So that's exactly the condition that, for very general points, that's exactly the condition that you have at least 10 points. Okay, and then we're gonna, so this is also, so we have K, which cuts a wall, and then there are all these other hyperplanes for different numerical rational classes on this side. On the other side, we don't know. I mean, we know that they have to be satisfying an inequality, d squared plus d times k is minus 2. Okay, and then we're going to look at chambers inside here and try to understand the corresponding moduli space. So I'll call these the k-negative chambers, the one that lie on this side of, on the k-negative side of K. Yes, it's not hard to prove directly, and this is our situation, that if I pick any ample liminal, which is even nef, yes, pick something that's nef, then, but with the self-intersection strictly positive, that there can be only finitely many of these hyperplanes that pass through it. And then you can ask the same question: what happens for liminals that are nef, maybe ample, that lie on K perp? So there it's not true that there are only finitely many walls if, sorry, what am I going to say? Let me take that back. So as I said, so if you take something nef that with positive self-intersection, there are finitely many walls that pass through it. If the self-intersection is 0, that's not anymore true. So when we have exactly 9 points, then those will there will be one. Okay, so there will be many of those that lying on this hyperplane, for example. Okay. Okay. So then, so what happens when you cross one of these walls that are that contain something on the k-negative side? So in this case, there's a controlled picture, which again it's results from of Goethe and Maruyama and Friedman Chin. Yeah, so I'm gonna look at the wall, what I call a k-negative wall. Okay, and so I have a chamber that's negative, where the liminals are negative with respect to 2D plus k, and a chamber where these are positive. So you can pick any liminal there, L minus, L plus, and then you cross somewhere at some other liminal L0. And let's assume for simplicity that you cross only one wall at a time. So it means that here I will have a strictly mu L0 semi-stable object, and that these come from extensions of the type, extensions of line models of O of D by O of minus k minus D. And you can look at the space of such extensions. I'll call this P lower D, and you can compute dimensions. And the dimension here is minus d square. So if d square is positive, then there will be no such extensions. And then what happens is that all these spaces, yeah, so these are strictly semi-stable with respect to this L0, but at least from this sequence you don't see any obvious violation of stability for liminals that lie on the negative side, and it turns out that there are none. So there is no, so these will lie in the, these will all be L minus stable. So all this projective space, if not empty, lives in the moduli space, which I call MC minus. But then this is clearly also will violate stability for all the liminals that lie on the positive side. So this will be something. This will be mu L minus stable, not mu L plus stable, and strictly mu L0 semi-stable. Okay, so what happens? So that means that if you want to moduli, to understand what happens with the moduli space on the other side, all these extensions have to disappear, and basically you replace them by switching, looking at extensions where these terms are switched. Okay, so, and then there is a small calculation using the fact that you do have really a k-negative wall. To give a bound on the possible numerical rational classes that can appear. So d square is bounded from by 1, and just by the same estimate, by replacing d with minus k minus d, you get this has to be also bigger or equal than minus n. So this also shows that this space of extensions could, and all these cases can happen. And then, yeah, this shows that this could be empty also. So similarly, yes, you have a claim that the same space of extensions, but with the term switched, will lie in the moduli space corresponding to the positive chamber. Okay, so this will lie in the moduli space corresponding to the positive chamber. And more than that, whenever these spaces are not empty, that's all you have to do to get all the stable objects on the positive side. So this is, again, it's a classical theorem that I will just state like this. So the statement is that whenever this makes sense, this is true. So the blow up of the moduli space on the negative side along this space of extensions is isomorphic to the blow up of the moduli space on the positive side along this space of extensions. So that means for both sides to make sense, I need to avoid the extreme cases here. Yes, but whenever these are not empty, then I can talk about this. And then more than that, you can you get that this is either you get an explicit small modification sometimes, and sometimes a blow up. So there is a rational map, a birational map, which I call phi, which is exactly so I'm saying here also that it's the same exception divisor that you can blow down in a different way. So blowing up this projective space and then blowing down the exceptional divisor, you can do that such that is the exception that you blow down to exactly this projective space of extensions. And note also that these are, when you compare with the moduli space of slope semi-stable objects with respect to a line bundle that lies on the wall, these spaces of extensions represent the same object. So it's the object with even at the level of slope semi-stability. This is just the object which is a direct sum of these two line bundles. So this is a point. This is a point. Yeah, so I didn't tell you how to identify objects in the moduli space of slope semi-stable things, but this will be true there too. So and it's a bit subtle. So what happens here? So this can be depending on d square. If you're not right in the middle of the possible range, then actually it can happen that that these moduli spaces are actually isomorphic to the you can compare what happens with the Gieseker stability with respect to this line bundle, and sometimes you get one of these moduli spaces. But anyway, so I'm saying that it's quite explicit, and then when you can say when this is a small modification, namely, yes, when none of these spaces is a point, so I'll write this down. But so when one of these spaces is a point, this is actually the map is a blow up of that point. So either phi or its inverse is going to be a blow up of a point. Again, this is part of the general theory. Okay. So I'll say when, so I'll be precise. So if d square is, I avoid the two end cases, then this phi is really a small modification. Yeah, this is immediate from what I said before. And then if, for example, d square is 0, then and what I was saying was that this is actually the blow up. You have on one side this projective space of dimension n minus 1. Okay. I didn't write this, I guess. So the dimension of p minus k minus d is n plus d square minus 1. Okay, this is in general. Okay, so this is getting blown down to the point PD. It's just a blow up. Okay, so similar when d square is minus n minus 1, which is the map goes the other way. And then the extreme cases basically correspond to one of these moduli spaces being empty. Okay, so if d square is 1, for example, then the moduli space on the negative side is empty. So PD is also empty. And then on the positive side, this is just this projective space of extensions. Okay, so I'm saying that now D, if you take D to be the hyperplane class, that's exactly the situation here. So I'm basically saying that all the extensions that you write down in this way, which are exactly of the type, yes, that you have on the right, or maybe, okay, so I want to say, yes, it's this one that that appears on the left, minus k minus h, and then h appears on the right. Yeah, so all these extensions will be stable for the positive side of 2h plus k. So you have the 2h plus k hyperplane. We already remarked that that on the k negative side, the moduli space is empty. This was the remark in the beginning, and then I'm saying that everything is stable on the other side. You can also check directly that stability is not violated by any torsion, by any subsheaf of E. And here you get Pn. Okay. Okay. So then what happens is that you can try to see what happens when you at the next walls that you that are neighboring this chamber. Okay, so explicitly, so let's look at a line in this vector space. So it's the simplest kind of symmetric class. So you take minus k, which need to be effective, but you add a multiple of the hyperplane class, positive. So this is just a plus 3h minus all the exceptional divisors. And then you want to classify all the stability walls that this line intersects. You have k perp of this line. And let's say we want to stay on the k negative side. We want to understand what happens there. Here A is n minus 5 over 3. There is the 2h plus k wall. So this intersects this line at a equal n plus 1. And then this is easy to calculate what are the possible numerical rational classes D that give you a hyperplane 2D plus K perp that intersects this line. There's some small computation you can do. And so then you see that, so this is explicit. You can compute all the values of A, all the D's. And then the first walls that you hit after this one, yeah, so here the moduli space was empty, here was Pn. The ones after are coming from classes of this type, so 2 times H minus EI plus K. So the D now is H minus EI. These are classes D with self-intersection 0. So they are numerical rational classes. They are classes of conics when you are on a Del Pezzo surface. They intersect minus K in 2, H minus EI. And then here you will have several of these because this is symmetric. So for all E's, you will cross the corresponding wall at this point. This is for A n minus 1. And then again, this explicit description of what happens when you cross a wall. Yes, what you blow up always some space of extensions. In this case, you blow up points, several points, and there is exactly n plus 4 points. Something that what you get at the next level is a blow up of Pn at n plus 4 points. And these are exactly the Gale dual points to the original configuration. Because in the last minutes of the previous lecture, I was saying how to describe the Gale dual points in terms of extensions. And those were extensions that admit a subsheaf, a subbundle of this type, of H minus EI. And now this is exactly the kind of extension of this type for one of these H minus EI classes. So you go from Pn to the blob of Pn plus 4. Yeah, so I'm basically saying that you get the blob of Pn at the Gale dual points as a moduli space. And then you can continue this in a similar way. Yeah, so the next one will be classes of this type, EI minus EJ. So these are minus 1 classes on the surface. So these will correspond to flips. Yes, as we said, if d square is in between these values, so let's look at the minus 1 and bigger than minus and minus 2. This is a small modification. So you will flip one space of extension, which is P1. It's actually the line through the 2 points Pi and Pj. And then you replace it with the projective space of dimension n minus 2. Okay. All right. Okay. So let me say that you can classify some of these classes for the first few values of the self-intersection. Okay, so maybe something that you can talk about lines, conics, and cubics, just like the way you do for Del Pezzo surfaces. So if I take some numerical rational class with the correct self-intersection, okay, so we say that D is a line, numerical line, if the self-intersection is minus 1 and the intersection with minus k is 1. Say this is a conic, numerical one. If d square is 0, d times minus k is 2. And then the cubics which is self-intersection 1, and intersection with minus k is 3. You can classify these as long as they define a k-negative wall. You can prove that for any number of points, yes, these classes will be effective, and then it's a classical argument like Nutter's inequality to prove that these are really just elements in the orbit of an exceptional divisor. These are again in the Weyl orbit of a usual conic and the usual cubic. When you have at most 9 points, this is the actual classification. You can, when you have at most 9 points, you can also classify -2 classes as the next case here. So classes with self-intersection -2, when you have exactly 9 points, are in the orbit of one -2 class, like a difference of two different EIs. Okay. Okay. So let me just state a theorem. For which I need to define a region in the Neff cone that we want that correspond to the non-empty moduli spaces. So notation is that if you look in the Neff cone of the surface, the blob of P2 at n plus 4 points, I want to always look only on the k negative side. Then I want to make sure that that this condition, this necessary condition for non-emptiness is satisfied. So for any cubic class, I want this intersection of L with 2b plus k to be bigger or equal than 0 for any cubic b. So any cubic means any element in the orbit under the Weyl group of the hyperplane class. Okay, so this is a closed subcone in the k-negative part of the Neff cone. And then I want to look at the part where I eliminate. I want to be always. So on this region, I want to look only at chambers where a small modification happens. So no blow-ups. This is the Neff classes, which are intersecting minus k non-negatively. Now I want to have the condition on that for any conic, numerical conic, I'm always on the positive side of the walls cut by conics. And one cone is contained in the other just by this classification. Okay. Okay, so then the theorem, and then I'll finish with that. Okay, I won't go into the details of this. Yeah, this is with Carolina Araujo, Indar, Kaur, and Diletta Martinelli. So is that there is an isomorphism between the Néron-Severi vector spaces of S and X, such that the canonical class is mapped to the canonical class. This respects the positive side and the negative side. So now we're looking at the intersection pairing on the surface and the Coble pairing on X. This is not an isometry, but if you restrict to the orthogonal complement of the canonical class and multiply with 1/2. This is the canonical isometry between these lattices K perp on both sides. This comes from this identification of the roots. And then this map has a geometric meaning. So when you take L in a chamber, this is mapped to what's called the determinant line bundle on the moduli space. This is the what is used to prove that the moduli space is projective. So this is ample on the moduli space. Okay. There are also things you can say about for ample line bundles which are not in a chamber but on a wall, and how to compare the respective determinant line bundles. So that's the heart of this proof. In fact, to understand this well enough to be able to write down this map explicitly. And then the properties of these cones that I introduce is that these are the cones that correspond to the movable cone on the k negative side. So understanding the k negative side of the movable cone is equivalent to understanding this subcone there. Same thing for the effective cone. Again, always on the k negative side. And more than that, so you can essentially identify stability chambers with Mori chambers in this region. So stability chambers correspond to Mori chambers. It's 1-to-1. On the k negative side. Then stability chambers in the k negative side as well, but okay. So in other words, I mean, I defined my cones here already as subcones of the k negative side of the Neff cone, but okay. And then you can say more precisely that if you have some chamber, a k negative chamber, then this map will map its closure to the Neff cone of the corresponding model. And as I said, you can say a few things about if these cones lie strictly on the k negative side, they will be finally generated by semi-ample divisors, and then it can happen that that's not true. Already for the case of 9 points. Okay, I think that's all I want to say, so I think I'll stop here.